Welcome to AI News. Real people, ethical AI, and top-notch intellect. Unleash your intellectual spirit with artificial intelligence news.
What if the future of computing could solve problems that even the fastest classical supercomputers couldn't crack in millions of years? Imagine a world where the computing power goes beyond binary states, where it takes on a quantum guise. This isn't a far-off fantasy, it's a reality that's taking shape right now, with the IBM Quantum System 2 leading the charge. Picture it, a behemoth sheathed in grey metal, roughly the size and shape of an industrial refrigerator. It hums quietly, an electronic lullaby that belies the extraordinary power within. Inside, 3 IBM Heron quantum processors, colder than deep space, work in unison, making the system a significant step forward in the quantum computing revolution. With hundreds of qubits operating on 3 connected processors, the Quantum System 2 seems to be a formidable player in the world of quantum computing. Appearances can be deceiving, especially in the world of quantum computing. Take, for instance, the qubits in the IBM Quantum System 2. These tiny workhorses of quantum computing are not as indestructible as the fortress-like exterior of the System 2 might suggest. Quite the contrary, these qubits are sensitive, more so than your favorite celebrity on social media. To do their quantum magic, qubits must maintain a state that is as fickle as it is fascinating. This state is known as superposition, a concept that quantum physics borrowed from the world of dreams. In this state, a qubit can be in multiple states at the same time, much like how you can dream of being at 2 places at once. But here's the tricky part. Any slight increase in temperature, any tiny tremor, or even a whisper of noise can disrupt this delicate state. That's why quantum computers like the System 2 need to be kept colder than the deep, dark void of outer space, where silence reigns supreme. Yet, even in such perfect conditions, qubits are prone to errors. These errors are an obstacle that quantum computing pioneers need to overcome to make quantum computing a practical reality. As impressive as the Quantum System 2 looks, it still represents the early stages of the quantum computing revolution. But don't be disheartened. Every revolution starts with a single step, and we've taken more than just a few in the quantum world. Quantum computing is a race that requires significant investment and overcoming serious technical challenges. The finish line? A quantum computer big and reliable enough to meet the demands of business, ready to solve problems that even the fastest classical supercomputers couldn't crack in millions of years. In the starting blocks, we have heavyweights like IBM, Google, and Honeywell. Each is committed to this journey, ready to invest billions of dollars in a bid to outpace the others. IBM's Quantum System 2, for example, represents a significant step forward, despite it being more akin to a 1960s-era CDC 6600 than a modern supercomputer. But this isn't a sprint, it's a marathon. As IBM's Senior Vice President Dario Gil puts it, we've been on this journey for many years, and we're going to be on it for many more years. So buckle up, because the quantum race is on, and we're just getting started. The distinction between a classical computer and a quantum computer starts at the most fundamental level. You see, classical computers, such as your laptop or the supercomputers in high-tech labs, operate on bits. These bits exist in a binary state. They're either on or off, represented by a 1 or a 0. Now, let's talk about quantum computers. They use something called qubits, not bits. The magic of qubits lies in their ability to exist in multiple states at the same time, thanks to the peculiar properties of quantum physics. Imagine being able to be in 2 places at once, or do multiple tasks simultaneously. That's what qubits can do, at least in a quantum sense. This unique property allows quantum machines to perform a multitude of calculations at once, providing a level of parallelism that is simply unattainable with classical machines. Picture a classical computer as a very well-organized office worker, going through tasks one by one. Now imagine a quantum computer as an entire team of office workers, all tackling different tasks at the same time. So why does this matter? Well, this leap doesn't just mean faster computations. It signifies a paradigm shift in how we approach information and computation, opening up a world of possibilities for solving complex problems. Quantum computing is not just about speed, it's about a whole new way of thinking about information and computation.